Alright, so we're looking at section 1.8, which is an introduction to linear transformations. So we talked about how we have this matrix equation, and then we also have these weighted vectors, and we're just pretty much saying the same thing. It's just different ways of writing the same thing. So we can have this matrix equation where we have So we have this matrix equation where we have ax equals b and au equals 0. So when we take our vector x, multiply it by our matrix A, then we get out the vector b. And we take our vector u, multiply it by our matrix A, we get out the 0 vector. And we're going from our 4 space to our 2 space. So this is transforming vectors with this matrix multiplication. And this transformation that's happening, we can also call it a function or a mapping, is going to take a vector in our n, and we're going to map it to, or take it to, like if we take our function t of x, then we're going to get out a vector t of x in our m space. So this transformation that we're doing here is taking a mapping from R4 to R2. And then some vocabulary, we have the domain, which is where we're starting. And then our codomain, which is all of the Rm space. But then the range is where in our codomain our transformation is taking us to. So the range is contained in the codomain, and the range is the set of all the images. So looking at this matrix A, and what we have here, we have a matrix, or we have a vector u in R2, vector b and c in R3. And let's define its transformation t that goes from R2 as its domain to R3 as its codomain by our multiplication by matrix A. So we need to find t of u, the image of u under our transformation t. Find an x in R2 whose image under t is b. Is there more than one x whose image under t is b, this b over here? And let's also determine if c is in the range of the transformation t. So pause the video, try this, and then we'll talk about it. So in order to find t of u, we just need to take a and multiply it by our vector u. So let's try that in MATLAB. So what I have is matrix A, and then I have vector u, and I'm going to make it as 2, -1, but then I'm going to transpose it so I get a column. And then I have a times u, and what's that going to be? 5, 1, -9. So I'm going to have our transformation on u is going to give us 5, 1, -9. For finding an x in R2 whose image under t is b, we need to take this a, and then we need b to give us an augmented matrix. And then we can do row reduction to get our solution. So let's try that in MATLAB. So we have b is going to be 3, 2, -5. And then we're going to make that a column. And then we're going to make a new matrix where we're going to set that as A, B. And so we have A first, and then we have B as our augmented part of our matrix M. And then we can row reduce on matrix M to get this. So from our row reduced augmented matrix, we know that x1 is going to be 1.5, and x2 is going to be -0.5, and so our x is going to give us 1.5, -0.5. And this is the image of this x that we have. Under t is given the given vector b, right there. So the question is there more than one x whose image under T is B? And so any x, is there more than one x? And so from here, we can see, well, this is a unique solution. So we don't have infinitely many solutions because we don't have a free variable. So we have only one x. It's unique. And then determine if C is in the range of our transformation T. So I think we need to do something similar with this and the C that we have here. And let's try that in MATLAB as well. So just like before, we're going to take our C, which is 3 to positive 5, and transpose that. And then we're going to ref on the matrix AC, and then we get that. So what does that tell us? That we have, wait, something happened. So what that's telling us, that we're getting out the identity matrix when we have AC, when we RF, we get the identity matrix. That means that on our last row here, we're getting 0 plus 0 equals 1, which means that our system is inconsistent, and so C is not in the range of our transformation T. This one right here. And you can kind of maybe think about predicting that because we have 3 to negative 5 is B, and then C is 3 to positive 5. So it's possible, you know, that just like that one change would give you something that's not going to work. So here we have matrix A, and we have that is 1, 0, 0 in the first row, 1, 0, 1 in the second row, but then our third row is all zeros. So what this does is it projects points. So it takes points in R3, projects them onto the plane in the x1, x2. So it zeroes out the x3. So whatever point we have, we just project it onto our x1, x2 plane, the flat one right here. So another kind of transformation that we have, because we had a projection up here, this is a projection. Well, what we have down here is a shear. So here's a sheep, and then here's a sheared sheep. And it's funny because shearing is what happens to sheep when you cut off all their wool. So that's not actually what a sheared sheep looks like, but it's the vocabulary word shear. So shear transformation is going to be where we take something that's like a square and then we shear it into a parallelogram in R2. But in different spaces it looks different. But what we can think about is we're taking this square and then we're transforming it into a different shape. But that's still going to be, and that's possible through multiplying by a matrix. So in this case, we have a matrix 1, 3, 0, 1, and then we are shearing each of these points for this square to give us the new points from our in our range. So, for example, if you look at the point 2, 2, so if you take a x where x is 2, 2, then where is that going to get us? It's going to give us 2, 2. So that's going to be 2 plus 6 is 8. And then 2 times 0 plus 2 times 1 is 2. So the place that we get to, our mapping, is to 8, 2. So this point gets mapped there. This point gets mapped here. and this point gets mapped there, and when we take our 0 vector, 0, 0 gets mapped back to 0, 0, because it's like our trivial multiplication. So that's a shear transformation. So apparently there are shear transformations in things like physics, geology, and crystallography, so these are just some images from the internet, but feel free to look some up, journal about them, maybe do something about shear transformations in your applications project coming up. Alright, so we have a definition, we have a linear transformation or linear mapping. If we have t of u plus v is t of u plus t of v for all of our vectors used in v's in our domain. And also scalar multiplication works the way that we think it will, where we have t of c times u is equal to c times t of u, where scalar multiplying can be factored out. So we alluded to it earlier, we have a transformation on our 0 vector. That's going to give us our 0 vector. Ooh, that's fun. It's harder to see though. So I got 0. T of c times u plus d times v, where t's are transformations, c and d are scalars, and then u and v are in R and space. This will give us c times t of u plus d times t of v. And the same thing goes here. Goes for here where we're taking a linear combination. So we have c1 times t of v1 plus dot 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 plus cp times t of v sub p. That's a vector. So that's for linear transformation. So what do you need to check to see if a transformation is linear? These things. So if we have R as a scalar, T is a mapping from R2 to R2, and T of X is the scalar R times X. T is called a contraction when you're going smaller, and then a dilation when R is greater than 1. So if we say that R is 3, how are we going to show that T is a linear transformation? Well, 3 times U plus V is going to give us 3 times U plus 3 times V. So that's going to be T of U plus T of V. So we're good on the first thing. And then, do we need anything else? No, because we don't have any other things to handle, right? I mean, we get 0, right? 3 times 0 is going to give us 0. So T of 0 is going to give us out 0. Alright, cool. So if we have this linear transformation, where we have 0, -1, and then 1, 0 as our matrix that is showing our linear transformation, what's going to happen? Well, we're going to swap our entries, like the first entry and the second entry change places, and we're negating the previous second entry, which is going to be our new first entry. So our images of under T of U, V, and U plus V, what are we going to do? Well, we just do this multiplication. So we have 0, 1, -1, 0 times U. That's 4, 1. And so that's going to give us, we're going to swap and negate our second, and we're going to put our first entry down in the second position. Alright? What about for V? So we have, again, 0, -1, 1, 0. We have 2, 3. So what's going to happen? We're going to have -3, and then we're going to have +2. And finally, what do we have for U plus V? What do we have for U plus V? We have U plus V is 6, 4. So then our transformation is going to be for 6, 4, we're swapping, so the the second row becomes the first row and it gets negated, and then the second entry is our first entry without a change in the sign. So geometrically, what's happening here? So if we have, change colors. So if we have 4, 1, so this is u, and then we're taking our image of u, and that's going to give us -1, +4. So this is our t of u. What about 2, 3? So what we have here, 2, 3, is going to be like up here, we have v. Then our image of v is going to be -3, 2. Oh, forgot parentheses. And then what about for u plus v? So we get, we have 6, 4, so that's out here, right? Taking our imaginary parallelogram. And then we're mapping it to -4, 6. So -4, 6 up here. And that's going to be, oh, this is u plus v, and this is t of u plus v. And this is, again, mapping with our little imaginary parallelogram that we have. So, yeah, there we go. It's fun to think about it geometrically. Parallelograms are really helpful, and that's, yeah. Oh wait, no, there's one more problem. So, we have two products, B and C, so let's call them Old Bay and then adobo, which doesn't have anything to do with C, but it's important that you know what adobo is. It's delicious. It's mostly garlic powder, but also, you know, some salt and other things. So, if you remember that we were talking about like unit cost of things, where we had materials, labor, and overhead that were represented for two different products for this company that's manufacturing stuff, and thinking about the cost per dollar of output. And we have our production vectors, which we can now think about in terms of a transformation, a mapping. So, we have this mapping, and it's a linear mapping, or a linear transformation, because if you're scaling up by like a factor of 4, what you're making, then your costs are also going to increase by that same factor. And this is like maybe not the best in terms of like a business model. I think that there's different ways to model cost increases, but it's interesting to think about. And then if we have our two different production vectors, then we can have our combined production is the sum of our transformation on those two vectors separately. So that's where the linearity of this mapping, or that we do have a linear mapping, comes into play. That we have scalar multiplication, and we also have addition working as expected. I think that's it. Public service announcement, please just try adobo. It makes popcorn really tasty. Also tahini. Tahini makes popcorn very tasty. And then the two of them together, very nice. Highly recommend.